Good evening, everyone. I'm Calvin Joseph, and today I'm going to conduct the week 10 problem solving and doubt clearing session for the course State Space Approach to Control System and System Design, which was taught by Professor A.P. Tiwari. Okay. So today I'll be discussing about the continuous time Kalman filter, about the tomorrow. Actually, the final equations will be sufficient. You don't need to study the derivation. Okay, so we will consider about the continuous time Kalman filter, the discrete time Kalman filter, and the exam paper also. This paper is surprisingly okay. So this paper is a pen and paper examination. So you will have to solve the sum. So there will be marks for the steps which we'll be using for solving the sum. Right. So you will have to know the formula, you have to write the equation, and you have to do step by step your mathematics, everything, and you have to get the answer. Okay. Also, there is some online calculator you have to use. I think that is similar to the gate calculator. So which you have to consider for the exam. Okay. So before going to the questions, I'll just touch briefly. Okay, so what Sir taught in this week was about the Kalman filter. And why the Kalman filter is there? Because in your real world, everything is not ideal. There is so much of noise, so many disturbances, and so many non-idealities are there. So even in the presence of all these non-idealities, even in the presence of noise, etc., we want to properly control our system. We want things to work fine. So for that, there's a person called Kalman. He developed a set of dynamical equations or a set of algorithm which we can use to eliminate the noise, to not eliminate the noise, to give us a best estimate of our states. Okay, so that is known as a Kalman filter. And sir had taught about state feedback. Sir had taught long back, and also sir said that if we are not able to measure all the states, we will use an observer. The observer will estimate the states, and using that estimated states, we can run the closed loop similar to state feedback. And we can do state feedback design separately, and we can do observer pole placement design also separately. There is a separation principle which is valid. But what happens is when there is noise. So if you will see this equation, we have x dot t is equal to ATXT plus BTUT plus VT. And y of t is CTXT plus WT. Okay, so these are noise. So this VT is assumed to come from your input. Okay, and this WT is assumed to come from the measurement of your output. Like when you're measuring the output, certain noise is being induced. And this VT is like something added up while you're giving an control input. VT is added to it. Okay. So there's an assumption that it is all the noise is white noise, that it doesn't have any particular frequency spectrum, and it is Gaussian and it has zero mean. So let me write some points. So today is week 10. The sir is teaching about Kalman filters. So this is a normal state space equation. C into x of t. What is added is some noise. Vt and Wt. Okay, these are certain noise terms which are added. So when there is noise, our what might happen is our control get corrupted by the noise which is affecting the system. And what we want to do is we want to, you know, we want to fight against the noise. We know that there's noise will be there in a real life system, but in spite of the noise, how do we get a good estimate of our states such that we can control our system well? Okay, so that is what is the role of Kalman filter. And this noise is assumed to be additive noise. It is added up. Okay, that's why there's a plus sign. Okay, so it is assumed to be Gaussian noise. So this is Gaussian noise. So what is like Gaussian or normal distribution is something like this. Okay, so it is assumed to have zero mean. That means there's zero. From that you have a sigma, minus sigma, standard deviation, etc. There are certain statistical ways to look at it. But what is the main thing which is considered is the distribution is a Gaussian distribution, and it has zero mean and some standard deviation sigma. So what is the the way how we will define a Gaussian noise, a Gaussian distribution is based on the mean and the standard deviation. So the marks of a person, the population, or many other things uh, we can we can show it, we can statistically put it in a data as a Gaussian distribution. And in our case, the noise which is added to the input as well as the noise which is comes when you are measuring the output is considered to be a Gaussian distribution. And the mean is zero. That means in an average sense, the noise is zero. But what could happen is the noise might make your measurement to be more higher than actually it is, or it could make it to be less higher. It could make it to be negative. But in the average sense, the noise is zero. Okay, the average value of the noise is zero. Okay. Okay, so then there's a mathematical thing known as expectation. Okay, so the expectation of Vt is zero, and this expectation of Vt into Vt transpose is Qt, delta t minus tau. Okay, so we will see how you look at it. And it is assumed that the noise at the input and the noise at the output are independent of each other. That is, they are not correlated. Okay, there's another thing which is known as correlation and covariance. So what is covariance of x comma y? It is something which will tell you how change in x is affected by changes in y and vice versa. Okay, so if covariance of x comma y is zero, that means x might change as here and there as possible, y will not be affected by the changes in x. Similarly, y can change in as many directions in as many possible ranges, but it will not affect x. Okay, and another way to look at it is written x is perpendicular to y. This is another way which is used to mean that the covariance of x comma y is zero. If the covariance of x comma y is greater than zero, what does it mean? Is an increase in x will result in an increase in y. Okay, if the covariance of x comma y is less than zero, it means an increase in x will result in a decrease in y, or an increase in y will result in the reduction in x. Okay, so that means it is negatively correlated or positively correlated. Okay, correlation is like basically a dependence on each other. Okay, so what they assume is this noise and this noise, they don't depend on each other. That is, the noise which is coming at my output as well as the noise which is coming at my input, they don't depend on each other. They don't affect each other, right? So that is another assumption. Okay. Similarly, the initial state also is not dependent on the noise. It is independent. So these were all the assumptions which were there. Like there are many assumptions which were there. And then there are various equations and various derivations which you don't need to know. You don't need to know all these equations and derivations. What you need to know is the final equations, like that is the final results, main results you need to remember. Okay, so uh, so what is the way is the final, the algorithm which Kalman filter will use. So they are considering a linear system, okay, and it is considered to be autonomous. For non-autonomous system where there is an external input, there are certain other changes which are there. Okay, so x dot of t is atxt plus vt, and y of t is ctxt plus wt. So what is assumed is qt, rt, and xt0 are known. So what is qt? Qt is the expectation of vt transpose vt, and rt is the expectation of wt into wt transpose. Okay, this is the expectation. So qt and rt is like kind of the noise distribution or the expectation of the noise, something like that. So pt0 is given by this. So this will be a square matrix. Then we will solve for p2. Okay. Then where p dot t is given by this equation. So it is a differential matrix Riccati equation, right? After they solve this, they will find the gain k e of t, which is minus of p inverse t, ct, r inverse t. And after that, they get the estimated state is obtained by solving xt dot t is at xt plus kt to ct xt minus yt. Okay. So this is the algorithm. So if you will see this algorithm, what you will understand is your k, that is your gain k, which is used over here, it is changing with time. It is dependent on time, right? Similarly, when we will consider a forced system, for a forced system also we will get similar equations. All right. This is shown over here. Then, now what happens if my ABC are constant and Q and R are constant? So we want to make things simple. Okay, when things are complicated, when everything is changing with time, it becomes difficult to analyze. So we'll consider linear time invariant system. Okay, ABC are constant, Q and R are constant, and T0 is minus infinity. That means we are considered that the system is at some state. With long back is the initial time. So what happens when we assume all this is this error covariance P is constant. And this is the equation which has to be solved. And once this equation is solved, we can get the gain K which is required. Okay, so there is this sum. This sum is there, which sir has solved it quite fast in some ways. Like we will be solving it again. Okay, we will be solving it again. So I have just re-modified this question. I've just written this question as a reference. Okay, so this is my system. X dot. Just hold on. Let me get the mic. So, are you able to hear me? So we go
Yes, sir. It is audible.
to check question one. Okay, what is the A matrix? Matrix is 0, 0, 1, minus 1, 0, 0, 1, minus 1. The B matrix is 1, 0, The C matrix is 0, 1. Okay, so this is for the system x dot t is a into x of t plus b into u of t plus bt y of t is c into x of t plus w of t. This is considered. Now, what is known as v of t is equal to r, sorry, is this q into delta t minus tau. V of t is q into delta t minus tau. So, what is done? The q, which is known as the expectation of v of t into v of t transpose, that's how it is written. Because they assume that this noise is coming from the input. So it becomes b into this q into b transpose. That is 1 0 q 1 0. So that becomes equal to q 0 0 0. Okay, so this is the resultant q matrix. Similarly, your r, which is related to your w of t, since it is just a unit, since it is scalar, it is not a vector, your r will be equal to r, it remains r. Okay, so now after we have this, what do we have to solve? We have to solve this equation. It is given by AP plus PA transpose minus PC transpose R equals CP plus Q equal to 0. This equation is given by AP plus PA transpose minus PC transpose minus PC transpose R inverse CP plus Q is equal to 0. N cross N. Okay, so let us. So you must remember that when we consider this matrix P, we will define it as P11, P12, P12, and P22. So it has to be a positive semi-definite matrix P, and it has to be symmetric. It has to be symmetric. That has to be made sure. So now if we do A into P, so 0, 0, 0, 0, 1 minus 1, 1 minus 1, P11, P12, P12, P22, plus P into A, so P11, P12, P12, P22 into A transpose. A transpose means 0, 1, 0 minus 1. Okay, this much is done. So this is equal to minus PC transpose R inverse CP plus Q. So this minus P1 and P12, P12, P22. C transpose is, which is C is 1, 0, 1, 0, 1. R inverse is 1 upon R, 0, 1 into P again. P11, P12, P12, P22 plus Q, which actually is Q 0, 0, 0, which is equal to 0, 0, 0, 0. So let us solve each of this one by one. So 0, 0 here is comes out to be 0, and this is 0. This is P11 minus P12, and this is P12 minus P22. This will come out to be 0, 0, P11 minus P12, this will be P12 minus P22. Plus, let us take the Q first. So this is Q 0, 0, 0. This, we will take this from the left hand side to the right hand side. So this will be equal to, this is equal to, go down. So this is what P11 into P12. So this is P12, P12 to P22. This is P22. This is 1 by R. This is 0 into, this is P12, and this is P22. Okay, so this, when you will add it, it will become Q, and this is P11 minus P12, P11 minus P12, and this is 2p12 minus 2p22 is equal to p12 square, so 1 by r is common, p12 into p22, p12 into p22, and this is p22 square. This is the resultant. So now we get three equations. Three equations we get. One is p12 square upon r is equal to q. Then p11 minus p12 is equal to 1 by r into p12 into p22, and 2p12 minus 2p22 is equal to p22 square upon r. So these are the equations we get. So what we'll do is we'll have p12 is equal to square root of r into q. So this is the first variable we get, that is p12. Okay. Now once we get p12, what we will do is we will try to get p22. So we get, how do we get p22? We do p22 square upon r plus 2p22 minus 2p12 is equal to 0. So this becomes p22 square plus 2r p22 minus 2r p12 is equal to 0. So we get p22 square plus 2r p22, and we will substitute value of 2r p12, p12 square of r3. So minus 2r square of r into q is equal to 0. So what we get, p22 is equal to minus 2r plus or minus square root of b square, that is 4r square minus 4ac, so plus 8 r square of r cube upon 2. So this we can write it as p22 is equal to minus 2r plus or minus square root of 4r square 1 plus 2 square root of q upon r. Okay, upon 2. So this we get it to be p22 is equal to minus 2r plus minus 2r square root of 1 plus 2 square root of q upon r upon 2. So we get p22 is equal to minus 1 plus or minus, minus r plus or minus r square root of 1 plus 2 square root of q upon r. We can write p22 is equal to r into 1 plus 2 square root of q upon r minus 1. Okay, so this is the value of p22 which we have computed. So we have got p12, p22. Now we have to get p11. So we get, what we can write, p11 is equal to p12 plus p12 into p22 upon r. Okay. So p11 is equal to p12 into 1 plus p22 upon r. So this is p12 into 1 plus r upon r into square root of 1 plus 2 square root of q upon r minus 1. Right? So this is p11 is equal to p12 into 1 plus 1 plus 1 into square root of 1 plus 2 square root of q upon r minus 1. So p11 is equal to p12, 1 minus 1 plus 1 plus square root of 1 plus 2 square root of q upon r. So we get p11 is equal to p12 into square root of 1 plus 2 square root of q upon r. So we get p11 is equal to p12. What is p12? P square of R cube. So this is square root of R cube into square root of 1 plus 2 square root of Q upon R. Okay, so are there any doubts in this?
No, sir. No.
So we have got this P matrix. Let's check what Sir has got. So Sir has got P12 is equal to square root of R cube. P22 is R into square root of 1 plus 2 square root of Q upon R minus 1. And P11 is equal to square root of R cube plus 2Q. Why is that? Okay. So it's simple. So Sir has just taken it inside. So it is square root of R cube into 1 plus 2 square root of Q upon R. That becomes equal to 1 cube plus 2 R1 square root of Q upon R. So this has become equal to 2 plus 2Q. Check. Also 2 plus 2Q. Just recheck my calculations. We've got three equations. P11 minus P12 is equal to 1 upon R P12 into P22. So P11 is equal to P12 plus P12 to P22 upon R. Okay, so we take P12 only. So that becomes equal to P12 into 1 plus P22 upon R. So 1 plus R becomes square root of 1 plus 2 square root of Q upon R minus 1. But my 1 and minus 1 get cancelled. So this 1 plus 2 square root of Q upon R. Okay. There is shown value. Equations. Okay, another thing I'd like to say is that this is a Zoom meeting which has a 10-minute, 40-minute limit since I don't have the premium version. So in another 10 minutes, the meeting will end. Then I will again restart the meeting with the same link. Okay, so you just have to rejoin the same. Right? So we got three equations. Let us see what they got. We want to square upon R equal to Q. They have got the same. Then P11 minus P12 is equal to P12 into P22 upon R. It is the same. And 2P12 minus 2P22 is equal to P22 square upon R. 2P12 minus 2P22 is equal to P22 square upon R. It is also the same. This also is the same. Mhm. Okay, let us see. Probably there's something wrong with this multiplication, but we'll check later. So this is the P11, P12 we get. Now we have to find the estimator gain. So the estimator gain is given by PC transpose R. And we just will see in the previous slides. We get a K is equal to minus P C into R inverse. Okay, K is minus P C into R. Is right. K is equal to minus P C into R inverse. This is what minus P11, P12, P12, P22. To what is our C? So C is 0, 1, 0, 1. R inverse is 1 upon R. So this becomes equal to 4 into column. This is 1, 4. This can be place. Mistake 1. P inverse CT into R inverse. Oh, this C transpose. Okay. C transpose. So this will be minus P C transpose R inverse. So this will get changed to 0, 1. So 2 will be 1 here. So this will be minus P12, and this is actually equal to minus P22. Okay, there's no minus, so plus plus 1R. So this becomes equal to minus P12 upon R and minus P22 upon R. Now this depends on our R and Q. What R and Q will select. So let us take R 0 to 2 and our Q, let us take it to be 8. Okay, if we do that, what do we get P12? So remember, P12 is equal to square root of R into Q. So that is square root of 2 into 8. That is given by square root of 16 is equal to 4. P22 on the other hand is R into square root of 1 plus 2 square root of Q upon R minus 1. So P22 is equal to R into square root of 1 plus 2 square root of Q upon R and then minus 1. Minus 1. So this R is 2 into square root of 1 plus 2 Q upon R 8 upon 2 minus 1. So this equals to P22 is equal to 2 into square root of 1 plus 2 square root of 4 then minus 1 is 2 square root of 1 plus 4 minus 1. So P22 is 2 into square root of 5 minus 1. So our gain K, which is given by minus P12 upon R minus P22 upon R. So what is my P12? Is it minus 4 upon R is 2 minus 2 into root 5 minus 1 upon 2. So this becomes equal to minus 2 and minus of square root of 5 minus 1. So can you calculate and tell me what is square root of 5 minus 1? Okay, it comes out to be minus 2 minus 1.236. So this is the gain A which it comes out. Now let us consider what is the matrix closed loop matrix. So if you will see this equation, if you will observe this equation, we have xc dot t is at xct plus kt into ct xct minus y. So what is the closed loop equation? Let us see. We have xc dot xc means the estimated state is at xct plus ket into c of t h of t minus y of t. Okay, so this becomes equal to at plus ket c of t into x of t minus ket into y of t. This is xc dot of t. Now, what is it in our case? In our case, we are considering an LTI system, linear time invariant system. So we have the equation x dot of t is equal to a plus kc into x of t plus q into y of t. This is our equation. So this one determines our closed loop stability or the stability of the Kalman filter. So we want our observer our state estimator to be stable. That is the bare minimum requirement we have to check. So let us check. So we have to do A plus KC and we have to find the outcome. So what is our A? A is 0, 0, 1 minus 1 plus K comes out to be minus 2 minus 126 minus 2 minus 126. What is our C? C is 1. C is 0 1. If I go to position is between 1 and 1. Use the transpose of the 0. This actually is 0 0 1 plus minus 2 minus 1.36 is 0 1. This is equal to 0 0 1 minus 1 plus 0 minus 2 0 minus 1.36. So this becomes 0 minus 2 1 is 1.36. Okay, so 2 minus 2.86. Let us find the rising values of this. This is A plus lambda I is equal to lambda 0 minus 1 lambda plus 2.86. So we have to find lambda I means A equals to equal 0. So we got lambda to lambda plus 2.36 plus 3 is equal to 0. That is lambda square 2.36 lambda plus 2. So we have to solve this equation. We will get the eigenvalues of the closed system. The meeting will end in 1 minute, so I will stop this meeting and I will again restart the same meeting, the same meeting. So kindly please do rejoin. Okay, so we have got the closed loop equation, statistic equation. So now we have to find the lambda which we have to get. So lambda is equal to. So in your exam, you will have to use the online calculator or you'll have to hand calculate it by yourself. So let us try. So the lambda is equal to minus 2.36. So minus 2.36. This square we have to use 4 AC, so that is 8, 2. Lambda is equal to 2.236 plus minus 1.36 square. So this becomes 3. It becomes plus minus square root of 3j upon 2. So lambda is equal to minus 1.118 plus or minus 1.732 upon 2. So plus minus 0.866 j. So these are these are complex eigenvalues with a negative real part. Okay, because they have a negative real part, that's why our system is stable. So are there any doubts in this? If any queries or any doubts in this sum, please ask. Consider this set of question. Okay, so I'll just give a recap of this sum. In this sum, let us look at the question. We have given it's an LTS system. Okay, in the exam, I'm assuming you will get LTS systems because LTV systems are very difficult. So it was also not solved or demonstrated LTV system, so I don't think you will come. So let us say this is a LTS system as come. You are given A matrix, B matrix, C matrix. Now they say covariance of additive white noise input is this. So you have to do B Q B transpose. You will get the matrix capital Q. Then R is not a matrix because the output is only one, so R is equal to small r. Then you have to use a matrix equation. What is the matrix equation which we have to use? We'll have to use this matrix equation. We'll have to use this one. was given. We have to solve this equation. AP plus PA transpose minus PC transpose R inverse CP plus P. And we have done earlier, like for state feedback and other things, that this P matrix should be positive definite. For it to be positive definite, P11 has to be greater than 0. And the determinant of the P matrix also should be greater than 0. So this thing you have to make sure that it is satisfied. This is not satisfied, then you have to fall. Okay? So that has to be taken care of very, very carefully. So that, because if you will notice, there can be multiple P12 can be negative also. Then there can be multiple options are possible. But you have to make sure you select such a P11, P22, and P12 as that your overall matrix is positive definite. And so that you have to take care. Then the K matrix is given by minus PC transpose R inverse. So you get the K matrix accordingly. They assume the value of Q and R, they get the K matrix is given like this. And the closed loop matrix is given by A plus K. So it has complex conjugate eigenvalues with negative real parts. That also is fine. Okay, so this for the continuous time Kalman filter. Now let us look for the discrete time filter. So now we are going by age of digital systems, and recently only there was one talk
Sir,
about.
can I ask a doubt?
Yeah, you can ask about.
Sir, can you show that Kalman filter gain once again? Is it P inverse C transpose R or P C transpose R inverse? Because in the slides also two at two places two different equations are.
Okay. So here was one P inverse C R inverse. Okay, and here it is given by P C transpose R inverse. Okay, so which one is correct? So let me just show. One is it saying minus P inverse C R inverse. Is it this one? Or K is minus P C transpose R inverse. Right? So if you will, one thing I'd like to tell is P inverse will also be 2 cross 2. P also will be 2 cross 2. But the issue which we are getting is C is actually 1 cross 2, which is not possible. You cannot multiply 2 cross 2 and 1 cross 2. But C transpose is actually 2 cross 1, which you can multiply. So this is the correct one.
Okay, sir, good.
This is one equation which you have to use. And you must use this A transpose P plus, no, actually AP plus PA transpose minus PC transpose I CP plus Q is equal to 0. And if you will carefully notice, if you do AP, no, AP actually is equal to, also you get your PA transpose is actually equal to your AP transpose. So whatever this matrix you get, just transpose it, you will get this matrix. So these are some simple things which you can do. No? Because this actually is what P transpose A transpose, and P transpose is equal to P. So this actually is P transpose. So it is a simple thing which you can consider. If, if you want to verify it, you verify it. So I remember when I was solving the sum at the start, I had forgotten to take this transpose and then I got a mistake and then I had to go back and track check. So these are some subtle things which you can keep in mind to prevent yourself from making mistakes. So this is the way to solve this thing for continuous time Kalman filters. Now let us go for discrete time Kalman filters. Okay, so I was just recently there was some talk in IT Kharagpur regarding the why digital is so important and why it is really picking up, etc. And this was mostly focused on digital VLSI, and they were saying that according there's something known as Moore's law. Which Moore's law was an Intel engineer or something, and he said that these IC chip size will keep on reducing as the days progress, and number of transistors per chip will increase a whole lot. But as they started, scaling down the size, the different technologies, and they started making it smaller, they saw that for analog design, it has reached a bottleneck. You cannot even make it any more small. But when you go for digital design, that size, that nanometer technology can be made even more smaller still. Okay, so that's why that person, an industrial person, was the industry expert was saying that if possible, you can try to digitize your system as much as is feasible, as is economical, and where it makes practical sense. Okay, because as you digitize it, there are lots of flexibilities which you can get with digital systems. Okay, so that is something. Just to give some motivation why we go for digital state control systems, as well as in digital technology in various other systems. Okay, so Kalman Filter was, if you saw earlier, was for continuous time conversion. When we go for a practical system, we are usually, or in most cases, we have a digital control system because we are going to use computers. And computers don't work in analog, they work in digital. If we make the sampling rate to be very, very small, we can get close to mimic analog, but it is not fully analog control, it is digital. And I think last week also, we had done a whole lot about various sampling techniques, multi-rate control, periodic feedback, and fast output sampling. These three techniques which are strong. So basically, things are going digital. So now we consider this time Kalman. We have this equation x dot p is ATXT plus BT and YT is CTXT. But when we discretize it, the right less xn plus 1 is phi n xn plus gamma n un plus qn and yn is cn xn plus wn. So in this case, this phi of n can be obtained by discretization of the previous matrix, etc. By first order or zero order approximation and gamma also can be similarly found. Okay, so these are the equations in discrete time. Okay, how to find this has been taught earlier. Now, the last few question. So V and omega I will represent the noise term. Vn is the noise which is added in the input, which is the input. Wn is the noise which is the noise comes when we are in the measurement of the output. Here, the system is considered to be linear. Okay, all these things are the assumption the system is linear, but it may not be necessary that it's time invariant. Because if it is time invariant, this could just be fine. It should just be camera. It is not dependent on time. But since it is dependent on it, it means it can be time invariant as well. So these are some properties of noise terms. This sample is white, is uncorrelated from instant to instant, and Gaussian and zero mean. All probability information is summed up in the covariance of the noise. So the statistical information for a Gaussian system is given by the standard deviation, etc., as well as by the mean. In this case, it is assumed that the mean is zero. This is the assumption which is there in the Kalman. Okay, and they have found it is important quite well for the systems and organizations. Let us assume it holds true. And there are various terms, etc., given over here, which are very advanced, very complicated. Right? So let us just assume certain things and that they are given. That's what solutions do. There are many mathematics over here, but let us just take the resultant and we proceed. Okay. They're saying an observer is defined by this x cap n plus 1, this phi n x cap n plus gamma n un plus k into y n plus c n x cap n. So x hat n is equal to the estimated state. So this is the actual state, one is the estimated state. And they are doing certain derivations. They did certain expectation, variance, covariance, optimum gain matrix they found, and various other things they have done. So they found it into a recursive form, and recursive form is very, very useful because we don't need to do the entire computation. We can find the previous output, previous estimated state, and we can use that to predict the next estimated state. And the previous estimated state has all the information of the past. It has the information of the past. So we no longer need to store all the past information. That information of the past is embedded in the previous estimated state or previous error, covariance, matrix, etc. And the information is there. So we just have to use this form of equation. Okay, this is the form of equation. So this is the final discrete time Kalman filter equation. So let us go over it one by one to try to understand what it means. So we go to what is known as the discrete time Kalman filter. Okay, by the way, Arun, you introduce yourself because I think you're joining for the first time. Are you a student? Are you working?
So actually, I'm in Samsung and I'm doing part-time PhD, and this is for my portion
You're doing part-time PhD where?
at MATLAB.
Okay, okay, okay. So you're from Kerala
Yes, sir.
and you're working there?
I am working in PPL Engineering College, Kollam.
Okay, okay, you're a professor. So this is part of your coursework or something? Like for your getting your credits?
This is a part of my mandatory course, sir.
Okay. Like, acha, you just part of your mandatory course. And how many such courses do you have to take?
Actually, I have to take 5 courses. One
Okay.
is research methodology. Other than that, 4 courses with credit. So currently I'm taking 3 courses plus research methodology.
Okay. So this course is in NPTEL. Other three courses also are NPTEL courses or they are taught in your college?
Research methodology is taught at NIT Calicut. The
Mhm.
second one is also NPTEL, Power Electronics, basically.
You are working power electronics. Power electronics what?
Yes, sir.
By which professor?
Power Electronics, DC converter. Kumara, sir.
Okay, it's very cool. You're working power electronics. Even in our lab, we are working on power electronics. So uh, actually, I am Professor Santanu Kapat's student. Probably have heard of his course.
Yes, sir. I had seen some videos, control and tuning methods in Power Electronics by Professor and
Yes, yes,
digital
yes.
control.
Yeah, exactly, exactly. So those
Right.
courses there. If
I
you want
think
to
in the
refer.
next semester, it will be open.
Okay, which one? The NPTEL one or the control and tuning one or the digital one?
Control and tuning one, I think it will be offered in next semester. I saw that in the next semester list.
You saw it where?
And tentative course list for next semester in NPTEL site.
Oh, okay, okay, okay. That's very good. Very good. See, my professor also was saying that that course might be floated again. So probably I might be the TA again over there. That's
Okay.
so because actually the digital course when it was floated that time I and my lab mate was a TA, but the NPTEL course was not floated. So now I think it is being refloated. So let us see.
No problem.
So this is the discrete time Kalman filter, and let us look at it. So what we have is we have a previous update state. Okay, this Kalman filter is it is going on. It is working in a loop. It is working based on recursion. Recursion. So we have previous updated state, which is xn hat. Okay, this xn hat. Now the first equation which is there, xn plus one tilde. So this is xn plus one tilde. This is phi n xn hat plus gamma n u of n. Okay, this is the equation. So this is known as the prediction. This is a prediction step. Okay, and this x hat n plus 1 is the known as the predicted state. So what what do we know? We know that our system, let us say our system is given by phi xn plus gamma un plus vn. This is stochastic. This is depends on noise, but this is the deterministic part. So we are using this deterministic part to find out the to predict the next state. Okay, what we're doing is we are using what we know for sure, or we feel that is quite accurate. We use that to find the predicted state. After that, what do we do is we will find the error covariance matrix, how it changes depending on the state. Okay, so how is that found? So that is P tilde n plus 1 is equal to phi n phi n into Pn, the previous estimated one, into phi n, I think it's transpose unit, phi n transpose plus Vn. So basically, this is dependent on the error covariance. So we are finding what is the predicted covariance matrix. I think I've written it down. Predicted covariance matrix. So this is the predicted covariance matrix. So this is the P tilde n plus 1. This is found. So this is step 1. This is step 2. Now you will go to the next step. What is the gain? Now this gain, K, depends on this predicted covariance matrix and this predicted state, as well as the output measured noise distribution. So that is written as K tilde n plus 1 is equal to P tilde n plus 1 into C transpose n plus 1 P n plus 1 P tilde n plus 1 C n plus 1 transpose and output C n plus 1 transpose plus W n plus 1 inverse. So this is the predicted gain, K tilde n plus 1. In the fourth step, this we are not considering. This I don't know why this equations are as, but this is not used anywhere else. This is not used anywhere else. So we can ignore this fourth equation. Because K hat n plus 1, which is found out through this, is not being used anywhere else. It is not being used anywhere else. I don't know why Sir has put it. So we will ignore this equation. We will ignore this fourth equation. We will go directly to the next equation. X hat n plus 1. Okay. So this is the state which we will update. So we have predicted some state x tilde n plus 1, but based on noise variance, those are matrix, as well as based on the current, what is the measured output and what is the output based on the estimated or the predicted state. We will do what is known as a correction. We will correct what is the state which we estimate. So we will write x hat n plus 1 is x tilde n plus 1, that is the predicted state, plus k tilde n plus 1 into what is the current measured output minus c n plus 1 into x tilde n plus 1. Okay, so this part is my predicted output. This part is my predicted output, and this part is my measured output. Okay, so I'll go on. So we first did a prediction step. We predicted what would be the state x hat x tilde n plus 1. Then we predicted the covariance matrix. Then we found out the gain, the expression for the gain we found. Then we used that expression over here, as well as we measure output and the predicted output, and then we do correction. This is known as the correction or the updated state based on the measure output, etc. After this, we do the fifth step, that is the updated matrix, the updated covariance matrix. So this we have the n plus 1 is equal to minus a tilde n plus 1 to c n plus 1 in n plus 1 in tilde n plus 1. This is the updated variance matrix. This is the updated covariance matrix. So we have seen this thing about this DT Kalman filter. So is there any doubt in this till now?
No, sir. Okay, it is okay.
Okay. So we'll solve a sum related to this. So we'll go to question 2. Okay. This is clear. Okay, so we have a system which is given by xn plus 1 is a into xn plus b into un plus bn. And our y is into cxn plus wn. So vn and wn are the noise terms. Okay. Is this linear time invariant, or does it depend on time?
It is not depending upon time.
Yeah, it is not depending on time because the ABC matrices are independent of n. Okay, so we have a matrix, B matrix, C matrix. So how many inputs are there for this system?
No, sorry, one input.
Yeah. How many outputs are there?
Put two outputs because C is 2 by.
Yes, there are two outputs, and that is also given over here. Measure output is y, 2 and 3. So it has two outputs, it has one input, and there are two states. Okay. Also, they have given what is this expectation of Vn transpose is given by 2, 1, 1, 3. An expectation of Wn transpose is also given. Okay, so kind of we have gotten what is the statistical information we need. So this is this expectation of Vn transpose is your capital Vn, and this expectation of Wn transpose is your capital Wn. Okay, so let me write it down. So your capital Vn is the expectation of Vn transpose, which is given by 2113. 2113. And your Wn is expectation of Wn transpose, which is given by 5336. 5336. So you must remember that these will be symmetric matrices. Okay, the off diagonal elements will be symmetric. You must make sure it will be. Okay. Next, they're saying the measure output is y, is 2, 3. So we have measured y at some particular instant. We got a measurement of y is 2 and 3. Very nice. Then we will see the predicted state. The predicted state in the Kalman filter algorithm, that is given by what? Your x tilde n plus 1. That is actually given by 1 minus 2. That is 1 minus 2. So this is the predicted state which our algorithm has done based on previous input, previous covariance matrix, based on various things, it has got that this is the predicted state. So this also is given. Also, we have got the covariance matrix is given by Pn is 5331. So our Pn is 5331. So this is the Pn matrix. Now they are telling us determine the predicted covariance matrix. We have to find what is the predicted covariance matrix, what is the gain K, and what is the updated state. So if you will see this sum carefully and recollect what I just told, it is related to the second, third, fourth step of your discrete-time Kalman filter algorithm. We are given the predicted state, x tilde n plus 1. We are told to find the predicted covariance matrix. Then we are told to find the gain. And then we are told to find what is the corrected state. Okay, now this is like when I saw these expressions, everything, you will be very shocked. What is phi n, what is gamma n, etc. And in our case, we don't have phi n and gamma. So if you will notice, in our case, that is in our sum, our xn plus 1 is axn plus bun plus bn, and y is cxn plus wn. So we have xn plus 1 is a into xn plus b into un plus bn. But in the discrete-time Kalman filter, the formulation of those equations, what they had considered was xn plus 1 is equal to phi n xn plus gamma n un plus v of n. Okay, this is what is considered. So what is our phi n is actually a, and what is the gamma n is actually b. And it is actually equal to phi and gamma because they are, phi and gamma because they are linear time invariant. It is a LTI system. It is no longer dependent on time. So this is phi and gamma. Okay. So the confusion, what is phi, what is gamma, is eliminated now. So now we have to do what is our step 2. Step 2. We have to find what is the predicted covariance matrix. So the P tilde n plus 1 is actually what A into Pn into A, I think A transpose plus Bn. So what is the A matrix? A matrix actually is 1, 2, 3, 5. 1, 2, 3, 5. What is the Pn matrix? Actually, it's over here. See, Pn is 5, 3, 3, 1. 5, 3, 3, 1. A transpose is 1, 2, 3, 5 plus Bn. Bn is what? Bn is 2, 1, 1, 3. 2, 1, 1, 3. Okay. So this is P tilde n plus 1. So P tilde n plus 1 will let us multiply. So 1 into 5 is 5 plus 2 into 3 is 6. 5 plus 6 is 11. So this is 3 plus 2, 5. 3 into 5, 15. And 15, so this is 30. 9 plus 5, it is 14. 1, 3, 2, 5 plus 2, 1, 1, 3. So we get P tilde n plus 1. 11 plus 10 is 21. 11 into 3, 33 plus 25 is 50, 58. 30 plus 28, so that comes up to 58. Okay, symmetric. 13 to 3, 19 plus 14 into 5, 17. So this is 140. This is 140 plus 2, 1, 1. So this becomes equal to 23, 59, 59, 140. So if you will observe carefully, that this also is symmetric. This also is symmetric. So these are things which you can use to verify your calculation again, so that you will know that you're on the right path. Okay. Or at least you will know that if you have made a blunder. Those are things to keep in mind. So we have got the first step, we have got a predicted covariance matrix P tilde n plus 1. Now we have to find the gain K. So the gain K is given by the expression we have just seen this one. K is P tilde, the predicted covariance matrix, into C transpose, into C into predicted covariance matrix into C transpose, plus WL. So let us go step by step. First, we'll write the equation. K is equal to P tilde n plus 1 into C transpose. Yes. C transpose has to be C transpose into C into P C transpose. So C into P tilde n plus 1 C transpose. Okay. This plus Wn plus 1, the inverse of it. So let us find this part. Okay. This part. So we have C P tilde n plus 1 C transpose. What is our C? I think it will be very complicated. C is 1003. So 1003. P tilde n plus 1 is 23, 59, 59, 143. Again, C transpose comes out to be 1003. This is a C. So what I'll suggest is to first do this multiplication. Because if you'll observe, this is the same thing here. So first do this multiplication. So what we will get is, we will get 1003. This 23 into 1 is 23. Okay. Then 59 into 3, it is 177. So maybe 59 into 1 is 59. And then 143 into 3. So that becomes equal to 9, 23 is 12, 21, 3 into, so it is 429. So this is 429. So this is very useful. Okay, this is what we want. This is what we want over here also. So that you can directly use next time. Then we have the C P tilde n plus 1 C transpose. Now we multiply this. 1 into 23 is 23. 1 0 into this is 177. 0 into 59 into 3 becomes equal to 177. Okay. 0 into 3, so 429 into 3. 429 into 3. This comes out with 1287. It is 1287. Again, if you will observe, this again is symmetric. Okay. Now, what we have to do? We have to do C P tilde n plus 1 C transpose plus Wn. That is 23, 177, 177, 1287 plus what is Wn? Wn is 5336. It is 5336. This becomes equal to 28, 177 plus 3 is 180, 180, 1287 plus 6 is 39. So this becomes 1293. Now we have to find the inverse of this. So C P tilde n plus 1 C transpose plus Wn inverse. For 2 cross 2 matrix, we interchange the diagonal elements. So this becomes 1293, 28. This becomes minus 180, divided by the determinant of this. That is 1293 into 28 minus 180 squared. That becomes equal to 3804. So this huge numbers we are dealing with, and these are because I have chosen some numbers randomly. That's why they come with difficult numbers. Okay, so now the next step is we have to find this K. So the K actually is equal to your this value. Okay, so that is 23, 177, 177, and 429 into this into this 1293 minus 180 minus 180 into 28, the whole thing divided by 3804. The K is actually equal to, these things require calculator only. This becomes equal to minus 2121, then 177 into 28. This is 816, so this also will be 816, and 177 to minus 180 plus 28 into 429. This is minus 19848. The whole thing divided by 3804. So this is the K matrix which we get. Okay, the last part is we have to find the updated state. Okay, I'm not dividing it because then it will become a bit difficult. So the last part is you have to find the updated state. So that is given by this equation. X tilde n plus 1 is x hat n plus 1 plus k hat n plus 1 into y n plus 1 minus c n plus 1. So this is the K matrix which we got. Now we will go the next step. Next step. This is the gain matrix which was found. Now we have to find the updated state. X hat n plus 1 is x tilde n plus 1 plus k plus k n plus 1 tilde into y n plus 1 minus c into x tilde n plus 1. Okay. So how do we get that? So what is x tilde n plus 1? We recall x tilde n plus 1 is 1 minus 2. This is 1 minus 2. This has the whole lot of the big, huge multiplication. Y n plus 1 is what? Y n plus 1 is 2, 3, 2, 3 minus c. C is into x tilde n plus 1. Okay. This C is 5, C is 1003, 1003 into 1 minus 4. Okay. So sorry, it's a bit messy, but this is 1 minus 2 plus minus 2121, 816, 816 minus 19848 into 2, 3 minus 1, and this will be minus 6. Okay. So this x hat n plus 1 is 1 minus 2 plus minus 2121, 816, 816 minus 19848, 1 and 9. And this becomes equal to 1 minus 2 plus minus 2121 plus 816 into 9. Minus 2121 plus 816 into 9. That becomes equal to 5223. Then we have 816 minus 9 into 19848. That is minus 177816. So our new predicted state is given by 5224 minus 177818.
Sir, I think you have missed that determinant in the denominator.
Oh, okay, okay, yes, yes, yes. So, big things. Yes, that is divided by 3804. So this also will be divided by 3804. That is why the state changed so rapidly. So we love this. This is 1 minus 2 plus 523 divided by 3 is 523 divided by 3 is 4 that will equal 1.3730. This minus 177.6 23 into 4 becomes equal to minus 46.744. So that becomes equal to 2.3730 and minus 48.744. Okay. So this is the next updated state. And this takes in all the information and gives us the next state which we will use in the next set of in the next iteration of my discrete-time Kalman filter algorithm. Okay. So any queries in this?
No, sir, it is okay.
So one thing I'd like to point out is the normal distribution, like the Gaussian distribution, is the normal distribution. Okay. And it depends on the mean and the standard deviation. So we assume the noise follows this pattern. Okay, the noise follows this pattern. Uh, what is the difference between the Kalman filter and the Leuenberger observer? So we have the Kalman filter and the Leuenberger observer. So Kalman filter's objective is to minimize the error, the square of the error. While the Leuenberger's observer is to minimize E of t. This will minimize E of t as t tends to infinity. Leuenberger observer does that. It is like asymptotically tries to make sure that the steady state error is driven to zero. Okay, as time t tends to infinity, the error E of t has to be goes to zero. In the Leuenberger observer, but the Leuenberger observer is a deterministic one. It doesn't take into consideration the noise and the other stuff which happens in the system. But the Kalman filter takes in consideration of the noise, assuming that it is a Gaussian distribution, that is, it is white noise, it is uncorrelated. That is the noise that now is not dependent on the noise previously or the noise which will come afterwards. That's what it means. So if you will see this notation, here, this one, expectation of Vn is equal to 0. This means that the average noise is 0 because it is a Gaussian distribution with 0 gain. Now this expectation of Vn transpose k, Vk transpose, depends on n. So if k is equal to n, that means that the noise at time 1 depends on the noise at time 1. That is true. But the noise at time 1 doesn't depend on the noise at time 0, as well as the noise at time 1 doesn't depend on the noise at time 2. They are not dependent. So that is why that expectation, that is that correlation, the covariance, is 0. Okay, that is what this means. Similarly, for the noise at the measurement, that average noise is 0. Secondly, that noise, measured noise at this time, at time 9, at time 7:30, depends on the noise at 7:30. But the noise, this measured noise at 7:30 doesn't depend on the noise, measured noise at 7 o'clock. It does not depend on that. Similarly, this measured noise at 7:30 does not depend on the measured noise at 8 o'clock. They are independent. So that's what these mathematical equations mean. That's their physical significance. Right? Similarly, what does it mean? V and W are independent of each other. That is, the noise at the noise at the input at 7:30 doesn't depend on the noise at the output at 7:30. Similarly, it doesn't depend on the noise at the output at 8 o'clock or at 7 o'clock. They're independent. So noise at the input is independent of the noise at the output, regardless of any time. Okay, at 7:30, the noise at the input doesn't depend on 7:30 at the noise at measured noise at the output at 7. Okay, this is what I'd like to tell. This is what these equations mean. Right? Okay. So are there any other doubts which you have? Questions regarding the exam for the stuff?
Uh, Sir, can you give an idea about the pattern of the exam? Okay. Is it how many questions will be there? Like that something can be uh, uh,
The difficulty with this course is like it is being rerun the first time. So
okay, okay,
there's not much information which is like previous data is not there for you to, get an estimate of how many questions, etc. will be there. So
okay, sir.
yeah, but what information are there to share on NPTEL is that it is like pen and paper. So first of all, that is like kind of difficult, right? Because now your steps also matter. What steps you
Yes,
have
yes.
done, they matter. Like previously to all the NPTEL courses which I taught, like I didn't know that there's this pen and paper type of exams also happen. So what used to be the focus was they should know a quick way to find the answer accurately. That was the focus. But here, I think it will be a bit different. And the way I recommend is, this is the way I recommend to solve any question in any subject is, you first read the question properly, and then you note down what is given. You note down your A, B, C. You note down that it is from this topic, whether it is from state feedback, whether it is from observer, all those things you note down. Okay, then you will get more clarity as to how to solve the question. Okay. Then if you know the formula for solving something, you write down the formula. Like this is the formula. A transpose P plus PA. Similarly, like that, the matrix Riccati equation, you write down that formula. And then you solve. Okay. And in these things, the sums are lengthy. I'll admit that the sums are lengthy. Like today, for solving two sums itself, we have taken so long. Hmm. So how many of these lengthy sums will come, we don't know. There is issue. But in the exam, since your focus is to get marks, you should start solving the easy sums. Easy sums, which it doesn't take much time, and you're confident on solving those sums. You start solving those sums. Once you get a grip and once you have made progress and once you've done what you know, then you can go to the harder and tricky questions. Okay. You should not get stuck at any question. You should not just say that I have to solve this question. No matter how much time it takes, I have to solve this question. If you do that, you have lost. You, you lose a lot of marks. Basically, target easy questions and try to work on it. And I'm hoping that there will not be this huge multiplication or the e raised to 80 find exponent, matrix exponent. I'm hoping that such questions should not be there. But I don't know like what the professor will decide and what he will set as a question. Okay? And since in the assignments you have many multiple choice questions are there, you have many multiple choice questions. You are you have questions which are select the correct option or options. You should read that carefully. So whether there is one correct answer or there are multiple correct answers. So there also so those questions will not take time. You just have to know the theory. You just need to select. So those questions could be scoring questions, I feel. Okay? And mm, I don't think sums will come as hard as in the assignment. Like some assignment questions were very difficult. You have fourth order system, that inverted pendulum, and you have M, you have this constant of the matrix, this constant of the system. I don't think such complicated sums will come in the exam because it is too difficult for a person to solve it using the calculator. Those basically are stuff which you should solve using MATLAB. Okay, so I'm hoping and I'm expecting that sums will not be, those entire big project type sums. Yeah, that's what I think. And we like to solve the assignments well, I feel. Solving the assignments will be very good. It will give you an idea of what questions will come in the exam. And you can do. One thing is you must know eigenvalue, then there are things about eigenvector and poles. Those basic things like controllability, observability, those might be easier to solve, easy questions also, which you have to look into. And yeah, that's there. Then any other topics like which you have found very difficult, something?
Sir, from that mathematical model, inverted pendulum, those systems,
No, yeah, yeah. The systems are it's true.
that week two assignment questions were
Oh, no, the element questions are really difficult. I don't know why they give it because afterwards, maybe you're not solving exactly those sums. So that's true. Those are very difficult questions. But I feel like it will not come that hard. That's my feeling. That feeling. But, no, you can never say it. Now, the Busker algorithm that should be known, uh, that can come. That is a thing which is deterministic. Your answer will be come. Okay? Poles, you should know where to place the poles when be given to a question. What are the transient parameters? What are the steady state specifications? How much should be the peak time overshoot? Based on that, you can find out where the poles are to be placed. Right? Those questions are there. Pole placement is important. Pole placement comes in state feedback. Pole placement comes in observer design. Right? Those are important. Okay. So that means state feedback. So, yeah. Because those are basic things. Those are easy things. So I don't think that would be much hard. Then you have the various canonical forms. That also is important. Uh, there are two, three canonical forms, Jordan diagonal form. These forms are important. How do you convert from one canonical form to another canonical form? Those things are easier. Okay, those are easier. Those are deterministic questions. They have a certain pattern that these are the certain steps you have to follow. Okay, those kind of questions you can strengthen. You can make it can be really laser sharp confident about it. So those things I feel would be useful. Uh, then any other topics you feel would be very, very important for schooling? Because I also have to conduct a summary session. There's a week 10. So I will have to conduct this 31st of March. So I'll have to conduct a session on 7th April, 14th April. Then I'll have another session I'll have where I'll have to give a summary of the course. So you could tell me like what topics you want me to stress on something so that I can prepare accordingly. So there will be a 1 hour summary session also held just before your exam. So that is basically to give you a revision. Which topics do you think would be needed for me to cover them?
Lyapunov stability,
Okay. Right. So one is the Lyapunov stability. Okay.
Then in multi-rate sampling, that computation of that C matrix, one problem was there in assignment also.
Okay, so multi-rate output controller, C matrix. So, sure. I think I have even solved it, right? I don't remember. I don't remember. Okay, MROC, C-bar matrix. Okay, then things which you feel were really important to discuss. Consider these basic things like state feedback. This should be very, very clear. State feedback, pole placement, controllability, observability. These should be known. Stabilizability, detectability, stability. Stability is very important. How do you find the stability? Various canonical forms,
LQR,
various LQR, linear coordinated relating. Yes, algebraic Riccati equation. This you should solve on your own. You should take an example sum ARE and solve it. Because you know there's a P matrix is there, no? P11, P12, P12, P22. And the problem is when you solve it, you have multiple solutions. You know, you will not know which solution you must consider, which solution you must discard. Like in our sum, we assume P12 is equal to square of alpha. What if I assume told that P12 to be equal to minus square of alpha? Then what will happen? So all those various cases are there. So right now, when we are seeing this question or seeing a solution or seeing someone solve it, these doubts will not pop up. But when we close the book, close everything else and try to solve on our own, like how we have to do in the exam, that time many questions will come, which will actually test how much you have understood, how much you have not understood. Okay, so algebraic Riccati equation, I'll say you have to solve one on your own. Do it on your own, get the three equations and solve. That is very, very important. LQR is there, canonical form, stability. What are the various things which we have considered? Okay, we'll see based on the right. Laplace transform also you should have done. Transfer functions will be there. Transfer function to state space to transfer function. That also is important. Transfer function to state space and vice versa. What is the state transition matrix? All these things you must look into. In the coming weeks, I will be teaching about the nuclear reactor control systems application for that, which is very, very specific for that application, but we will see like how whatever sir has taught in his entire course, sir will show him applying his techniques to the real world thing where he has worked extensively. Okay. And if you would have noticed that this is he has this FNA, so that is a very prestigious award is a very prestigious award for a person to get it. So what we could do is start here. Okay, and I'll admit I use MATLAB a lot. It has been very useful for me to solve sums. Like I use MATLAB for checking. Yeah, that is check. Exam you will not have MATLAB, but for solving the assignments, I do use MATLAB a lot. So what is the A matrix which we consider 0, 0, 1, minus 1, 0, 0, 1, minus 1, B is 1, 0, C is. Okay, and by the way, this recording and these notes will be uploaded. So this video will be uploaded on YouTube after I merge it, everything, etc. And these notes, these handwritten notes also I'll upload on the drive. So I hope you have access to it, right?
Yes, sir. Yes.
P is 0, 1, the ABC matrix, what is just given. Okay, Q equal to is we have question one. What did we have to solve? We have to solve this P matrix P1, P1, 2. We got the equations and we found these variables and this gain K. Closed loop stability also we got closed loop matrix, the eigenvalues. This is more or less, I think it's correct. Let us try question 2. Question 2 is what I want to check on. It's which is 1, 2, 3, 4, 3, 5. P matrix is 1, 3, 1, 3. P matrix is 1, 0, 0, 3. So it is 1, 0, 0, 3. So it is kind of like we are measuring each and every state. This is the ABC matrix we got. Notice our capital Bn is equal to 2, 1, 1, 3. 2, 2, 1, 1, 3. The Bn Wn is given by Wn is equal to 5, 3, 3, 6. 5, 3, 3, 6. Then the Yn, actually Yn plus 1. So Yn1 is measured is 2, 3, 2, 3. And x predicted in 1 is equal to 1 minus 2. 1 minus 2. This is what we have got. Now let us go to our steps just to recheck this. We have to find x. Okay, Pn also was given. Pn is 5331. Pn is actually 55331. This is a Pn matrix. Now let us find P tilde then plus 1. P predicted. So P predict n1 is equal to APN A transpose plus BN. A into PN into A transpose plus BN. Let us see what it comes out to be.
Capital P.
Oh, okay, okay, okay. Mhm. 23, 59, 59, 163. What did we get? 23, 59, 59, 143. They're saying 163. So where was the error I made? Oh, okay.
140 was
140. What was it? It was 13 to 3 is 90 and 14 to 5 7. Oh, it is 116. Okay. So, this is 160, this will be 163. Okay, even though we saw it is symmetric, the answer is wrong. Okay, so this was wrong. Let us find K. This is the K. So A is actually, since it is wrong, we will just complete. P n plus 1 C transpose. So it is P predicted and 1 into C transpose. So the transpose of C into the inverse of C P into C transpose. So it is whole thing. So it is C into P predicted M1 into transpose of C plus WN. We run this, what is K? K comes out with 0.2283, 0.0923 minus 0.1258 plus 0.37347. Okay, let's see what is our K. Our K came out to be this. So where is omega O? Just see this value is symmetric. This is also symmetric. Inverse of this is also symmetric. This into this is not symmetric. Okay, because the C matrix is not symmetric. Okay, so that's why it is not symmetric. So this is the predicted gains K, which are required. Okay, next is we find what is the updated state. So updated state is what? X update in 1 is X predicted in 1 plus K into the measured one, that is Y in 1 minus C into X predicted in 1. We have done this. So this is the next stage. So 2.0587, 1.003. Okay. When we got it 2.3743 minus 48.744. We made a huge deviation, which was quite suspicious as we look back and think. Okay, so I just write a note, mathematical, sorry, computational error. It's been computational error. Checked by your MATLAB. Okay, so all I can say is you have got to be careful while doing calculations, and at least MATLAB is useful for me to verify my calculations. But for you guys in the exams, it would be difficult, and you have to be very careful. Hopefully, the numbers and the values will not be very hard. Like the A matrix was full, the Q matrix was complete. So, like if you notice, this Vn, Wn were such high values, nothing was zero, etc. So if there's something zero, etc., it becomes easier to solve. So I hope such sums comes. Okay. So by the way, like you're familiar with MATLAB everything, right?
Yes, sir. Yes.
So I'll just do a brief recap and then we'll end the session. So we consider today the topic was regarding Kalman filters. There's continuous time Kalman filter, there's discrete time Kalman filters. And basically Kalman filters is there because there's noise in the actual practical system, noise at the input, noise at the output. And to overcome the noise from completely damaging our system or giving erroneous results, we have a Kalman filter, which is optimal state estimator to this point. Okay. So also it uses various mathematical statistics, terms, and points such as correlation, covariance, etc. We don't need to go much deep into all that, but we consider linear time invariant system, which was affected by the noise a little bit. By the affected by the noise, we got the Q matrix, the R matrix, etc. And then we solve the algebraic matrix Riccati equation, right? The algebraic matrix Riccati equation. Once we solved it, we got three equations. And then we found the solution of each and everything, P11, P12, P22, etc. After we got that, we found a K matrix, which is given by this formula minus P transpose C minus P C transpose R inverse. And after this was done, we substitute values of Q and R, which we considered, and we got the P1, their values. The effective K also was found. And then when we do this equation, we will get the stability depends on A plus KC. Okay? And the closed loop stability also we have checked. And we have found that the eigenvalues of this system, they are complex eigenvalues with negative real part. And we verified, we rechecked that the gain K is actually equal to minus P C transpose R inverse. This equation is correct, while this equation is not correct. Okay. Next, so when we have to solve this, this is the matrix Riccati equation, AP plus PA transpose minus PC transpose R inverse CP plus Q equal to 0, which has to be solved. And similarly, then you get K equal to minus PC transpose R inverse. Next is we consider discrete time Kalman filter, which has various update steps, etc. So this is the prediction step where we are predicting the value of the state. Then we predicted the covariance matrix. Then we determine the gain K, which we will use in our updating calculation. Then we updated the value of the state depending on the measure output and our predicted output and the computed gain. And then we updated the covariance matrix. And we did a sum where we consider Vn, omega n, the measure output, the predicted state, the covariance matrix. And then what did we find? We found the predicted covariance matrix we found. Then we found the gain K. And from that, later on, we found what is the update state, which is required for our calculations. So this was done, although I had made a silly mathematical error, which was found out through MATLAB. While we checked the lines of code, we were able to find what was the mistake which I had made. So I hope that you guys don't make this mistake. And then we checked, we had discussed Kalman filter measure is basically used to minimize this error, this mean square error over the time period, where the Lowenberg observer is basically for asymptotically we want the error to tend to 0. That is the concept of Lowenberg observer. And these are some topics. We just did a brief recap of what are the major topics which we considered in our session, considered in this NPTEL course. And these are certain important topics which I feel are easy to remember. They're easy to remember, the equations are simpler, which should be useful for you while approaching the exam. And the various advanced topics, I'd say you should be good with the concept, like what is the significance of this? Like what is the significance of the Kalman filter? What is the significance of multi-rate output control, periodic output feedback, or fast output sampling? Now, fast output sampling is a subset of multi-rate output control. Those basic concepts should be known. I think it's very hard or impossible to remember all the equations of this large stuff, but the basic, these equations I feel are easy to remember. These are things which can be spoken. Okay. So thank you for joining. I'll end this session.